Okay, so good evening, everyone. Team Parsec welcomes all of you to the second Astro Talk titled The Large Scale Structure of the Universe. Dr. Anand Narayanan obtained his master's and Ph.D. from the Department of Astronomy and Astrophysics, the Pennsylvania State University. In 2010, he joined the Department of Earth and Space Sciences, IIST. His research involves the study of diffuse gas in the intergalactic medium and outflow from active galactic nuclei with the help of spectroscopic observations. He had also anchored and scripted a 9-episode astronomy documentary series in Malayalam, which won the 2014 Kerala State Government Award for the Best Educational Program in Television. Also, he and his team made a 30-minute documentary which talks about the history of the 180-year-old Travancore Observatory and its importance. The documentary recently won the Best Researched and the Best Technically Visualized Film in the National Science Film Festival conducted by Vigyan Prasad. The link for the talk will be found in the Parsec WhatsApp group. So I request all of you to keep your mics and videos turned off until the end. If there are any questions, you can put it up in the chat box. So without any further ado, let's get the talk started. Over to you, sir.
Thank you, Arjun. Thanks, Parsec, for this invitation. Although IIST and IISER are geographically very close, I've never had the chance to come to IISER, but I know a lot of people, students and faculty members at IISER. So it's finally good to be able to connect, although virtually. So I'll start my presentation. Just share the. Is the screen visible in full?
Yes, sir, it's visible.
Yes, okay. So today's presentation is about the large-scale structure of the universe, how astronomers carefully mapped what is the three-dimensional geometry of our universe, primarily through galaxy redshift surveys. Okay. So any kind of measurement in astronomy is very difficult, and that is because of the enormous distances that separate us from the objects that we are studying. And looking up at the night sky, it may seem as though the stars and galaxies are spread out in a more or less random fashion. But we know that this is not really the case. The universe is not just a random jumble of objects. There is a structure, there is a hierarchy of structure to it, of galaxies, galaxy groups, galaxy clusters, etc. And in today's presentation, what I'll be primarily talking about is how astronomers have carefully put together the 3D anatomy of the universe through long years of very painstaking observation. So since this is a presentation for primarily for all of you who are in IISER, okay, so I thought I'll just show a picture of the night sky photographed by Srira, who's a Ph.D. research scholar in IISER-Trivandrum. So this photograph was taken from IISER-Trivandrum, looking towards the center of the Milky Way galaxy. So which means that the field of view includes a part of the Sagittarius constellation. So the reason why I thought I will show this picture is to remind ourselves that there are an untold number of stars that we see in the sky, and we know that all the stars that we see with our unaided eye in the night sky, they all belong to our own galaxy, the Milky Way. Okay. And understanding the shape and size of the galaxy and where we are located within the galaxy, this has been a very, very difficult problem in astronomy, and that is because we are embedded within the galaxy. So it's like being stuck inside a house and not being able to go out. And if you were to ask to draw a map of how the house is going to look from outside, if you have never stepped outside, then it's going to be very, very difficult. Okay, so even understanding the shape and size of our own galaxy is observationally a very difficult problem. But astronomers have accomplished that by carefully mapping. Yeah, am I audible? Is there a...
Yes, sir, you are audible.
Yeah, so my internet, I just want to mention that my internet is connected through my phone. So if a phone call comes, then I may get disconnected for a few seconds, but I'll connect back quickly. Okay. So
Yeah,
as
yes,
I
sir, no
was
problem.
saying, yeah. So as I was saying, the understanding the architecture of our own Milky Way is difficult, but we know what our Milky Way looks like. Okay. So if we could take a journey out of the Milky Way, I'm sure all of you know this. This is very, very basic stuff. If you could take a journey outside of our Milky Way galaxies, you'll find that you're having some background noise because of the elections. Okay, so if you could travel outside of the Milky Way, we will see that all the stars, they are not, which we saw in the night sky, they are not just randomly distributed, but they are distributed with a planar geometry. And this disk-like geometry has substructure within it. There is a spiral structure to this disk. So we know now by carefully mapping the distances and positions of stars, star clusters, molecular clouds within our galaxy, etc., we know that our galaxy is a spiral galaxy. Okay? And this galaxy is not static, it is revolving. So there is a differential rotation to the Milky Way galaxy. This is also known by carefully measuring the kinematics of stars, gas, and dust within our own galaxy. So this is just a visualization of that. And Milky Way is not the only galaxy in the universe. There are other galaxies. The nearest big galaxy to the Milky Way is the Andromeda galaxy. So here is a quick zoom in into the Andromeda galaxy. Okay, so what you're seeing over here is the Milky Way galaxy itself. And during the months of December, January, of the sky, we will be able to see the Andromeda galaxy as a tiny smudge. But in reality, Andromeda is a galaxy that's as massive or more massive than the Milky Way, with more number of stars. And the reason why to a telescope or to our naked eye, the Andromeda appears as a tiny smudge is because of the enormous distance that separates us from Andromeda galaxy. The Andromeda galaxy is at a distance of roughly 2 million light years from us. So this is a zoom in onto the Andromeda galaxy. And if you do a survey of galaxies within the local volume of our universe, we encounter what is known as the local galactic group, which is a gravitationally bound entity. This local galactic group contains about 54 galaxies within a radius of about 3 megaparsec. Okay, so I don't think I need to explain what a parsec is here. Okay, so 3 megaparsec. And the two prominent galaxies that belong to the local group are the Milky Way galaxy and the Andromeda galaxy. These are the two big members of the local group. So our own Milky Way is part of a collection of galaxies, which we now refer to as the local group. And most of the galaxies in the local group are dwarf galaxies. And these dwarf galaxies are satellites to Milky Way and satellites to Andromeda. So all this information is known, but the survey of the discovery of dwarf galaxies in the local volume is not complete. Even as we speak, there are astronomers who are trying to pull out very faint, low mass, low luminosity dwarf galaxies within the local group. So there are discoveries happening of dwarf galaxies within the local group even now. Okay, so there is it's not done yet, but the local group is fairly well established as a gravitationally bound group. Now, a local group, in terms of galaxy grouping, local group is not really a big collection of galaxies. There are more massive virialized structures, gravitationally bound structures in our universe, and these are called galaxy clusters. So here is an example of the Virgo galaxy cluster. Okay, so all the dots that you see in this picture, most of them are stars within our own galaxy. The members of the Virgo galaxy cluster, which are galaxies, are all these extended objects that you see. Okay, so all the extended objects that you're seeing are members of this Virgo galaxy cluster. The point sources are stars within our own galaxy. So since we are sitting inside our galaxy and we are looking at something that's outside, extragalactic, whatever image we take, the stars within our own galaxy will also be there. And Virgo galaxy cluster contains about 1,500 galaxies, and it has a total dynamical mass of about 10 raised to 15 solar masses. Okay, so that's roughly 4 orders of magnitude more than the mass of the Milky Way, 3 to 4 orders of magnitude more than the mass of the Milky Way galaxy. That shows that there are about thousands of galaxies within this Virgo galaxy cluster. Now, Virgo is not the only galaxy cluster that we know of. There are a large number of galaxy clusters. In fact, there are galaxy cluster catalogs. So I'll just show you one more picture of what a galaxy cluster looks like. Okay, so this is the Coma galaxy cluster, which is much farther away from us than the Virgo cluster. And in this is a Hubble Space Telescope image. And in this, almost all the extended objects that you're seeing, they're all members of the Virgo Coma galaxy cluster, which means that these galaxies are roughly at the same distance from us, and they are gravitationally interacting, and probably they are all gravitationally bound structures. Okay, these 3 objects which we see with the spiky features, they are stars within our own galaxy, Milky Way. So I showed you all these pictures just to tell you that there seems to be a hierarchy to how matter is organized from the smaller scales to larger and larger scales. So there are some galaxies that exist in isolation. These are called field galaxies, but vast majority of the galaxies exist in groups and clusters. So then the question is, how does our universe look in a 3-dimension? Okay, so one way to answer that question is to carefully do a survey and map out the position of galaxies in the universe, which means where they are in the sky, and also establish the distances to those galaxies. Okay. So, how our universe looks in 3-dimension as far as the distribution of baryonic matter is concerned. Okay. So we have to map out the location of galaxies in space. We also need to map out how far away they are from us. Now, as you know, distances in astronomy are measured usually in units of light years, sometimes in parsec, in the case of galaxies in megaparsec. But a more frequently used unit, which as a proxy for distance, is redshift. Redshift is used as a proxy for distance, and that the reason is because the farther away a galaxy is from us, the higher would be its cosmological redshift. The higher would be the galaxies, the spectrum would be redshifted more. So redshift is often used as a proxy for distance in astronomy. So in terms of mapping the positions of galaxies in the universe, what can be done is we can find out their position on the celestial sphere, the right ascension and declination, which are the coordinates that astronomers use to pinpoint any location on the celestial sphere. And they can also measure the redshift of those galaxies. So this is what has been going on in extragalactic astronomy for quite a while. Different groups have been carrying out these large galaxy redshift surveys, where they try to look at, if possible, the entire sky. But if the entire sky is not possible, then they look at a large regions of sky, a quarter of the sky or a half of the celestial sphere, and try to map out the positions of galaxies in it. Now, the reason why it's very difficult to map out the entire sky is because we have to use telescopes for that, and telescopes are geographically located either in the northern hemisphere or in the southern hemisphere. There are not many, there are some telescopes which are closer to the equator, but most of the telescopes are a little bit off the equator, either north of the equator or south of the equator. So once your telescope is positioned in a geographical location, you cannot have access to the entire sky. So from ground-based facilities, it's very difficult to, from single ground-based facilities, it's very difficult to carry out all sky surveys. You have to use multiple telescopes. Okay. So what I will be doing next is I'll be talking about one of these galaxy redshift surveys, a very prestigious survey, which is called the Sloan Digital Sky Survey. Short form of that is SDSS, the Sloan Digital Sky Survey. Am I audible? Sorry, in between a phone call came. I had to cut it.
Yeah, you're audible, no problem.
Okay, yeah. So this is the picture of the Apache Point Observatory. This is the telescope that is, this is the 2.5 meter telescope that is located in a place called New Mexico in the US. It's an arid place, so which means that the sky is more or less clear. Okay. Sky is more or less clear, and this particular observatory was exclusively used for the Sloan Digital Sky Survey. So it's a sky survey to map the positions of galaxies and also stars in roughly 1/4 of the sky. And so this particular telescope was used, and the observational strategy that SDSS used is something very interesting. So I would like to take about 5 minutes or so to explain the behind the scenes of the Sloan Digital Sky Survey, how the observations were accomplished. Now, in order to know the position of galaxies in the sky, we need to take images, that is photographs. So that we need a CCD camera that is connected to the telescope. Okay. So the CCD camera, where the telescope will collect the light and it will focus the light onto the focal plane of the telescope, and the CCD camera will render the image. Will collect those photons and it will render the image. So by photographs will help us identify point sources and extended sources like galaxies in a given field of view. And by changing the field of view, you can cover a large patch of the sky. Okay, one quarter of the sky in the case of SDSS. So that will only tell us where the galaxies are located in the sky. We also need to know, if you want to know the 3D architecture of the universe, we also need to know how far away these galaxies are from us. And for that, we need to measure their redshift. And in order to measure the redshift, we need to record the spectrum of these galaxies. Okay, so which means we need a spectrograph. So what the basic architecture is that the telescope will collect the light, and the light will be sent to the spectrograph. The spectrograph will have a dispersing element, typically a grating, and the grating will disperse the light, and the dispersed light will be captured by the CCD camera. And so you have a recording of the spectrum of that object. Now, why is spectrum important for determining redshift? Because if the galaxy is moving away from us, then the spectral lines present in the galaxy's spectrum would be systematically redshifted. Okay? And so you can measure how much the absorption lines and sometimes emission lines in the galaxy spectra are shifted, and that shift can be used to establish the redshift of the galaxy. So spectroscopic measurements are required to accurately determine the redshifts of galaxies. So there has to be a spectrograph also. Now, the difficulty, the challenge with large surveys like SDSS is that in order to come up with a statistically significant sample of galaxies in the universe, so that you can map out the 3D architecture of the universe, you need to observe hundreds of millions of galaxies. So if you keep on looking at one galaxy at a time, it's going to take a lot of telescope time, and it's going to take a lot of time to finish the survey. Okay? So what the Sloan Digital Sky Survey did is they adopted a technique which is called multi-object spectroscopy, and the multi-object spectroscopy works. Before I show the animation, I'll just explain what it is. So in this SDSS survey, what they did is they took large aluminum plates, okay, plates that are made of aluminum, which are very lightweight, and they took images of patches of sky, okay, that they wanted to cover, and these images were taken over multiple nights, over multiple weeks, over multiple months. So whenever they take an image, and when they analyze that image, they know in that patch of the sky where all objects are present, specifically galaxies, where all galaxies are present. And then what they do is they take this aluminum plate and they put holes in that aluminum plate corresponding to the location of galaxies in that patch of the sky. So they will puncture holes in this aluminum plate. Okay, so now if you mount this aluminum plate at the focal plane of the telescope, then essentially the light that is going to come through the aluminum plate will be only light from those galaxies that are present in that patch of the sky. So it's like small slits, okay, which are looking at a patch of the sky. So these holes will be looking at individual galaxies in that particular patch of the sky. When you move to a different patch of the sky, you will have to put new holes on it, or take a new plate and put new holes on it. So now these holes are put. Now what they do is they connect to each hole on the aluminum plate an optical fiber. And this optical fiber, so what happens is through that small slit, through the small hole, the light from the galaxy will enter. And this optical fiber will take that light onto the spectrograph. Okay? And the spectrographs will disperse that light, and the dispersed light is imaged by the CCD camera. The interesting thing is each of the holes is looking at a galaxy, and each of those holes are connected with an optical fiber, which means in one go, the telescope is looking at a large number of galaxies in a certain patch of the sky, and in that one go, all those galaxy light is brought to the spectrograph, and the spectrograph simultaneously disperses the light, and all that dispersed light is captured by a wide field camera. Okay, so in one shot, you get the spectrum, low resolution spectrum of a lot of galaxies present in that field of view. So this really amplifies the speed with which this survey can be done. This technique is called fiber-fed multi-object spectroscopy. Okay, so fiber-fed meaning the light is being fed by optical fibers, and you're looking at multiple objects in a single pointing. So the multi-object spectroscopy. Okay, so I'll just show you a video of this entire thing. And initially in this video, what you will see is the dome of the telescope opening and the telescope coming into our view. And then you will see an astronomer going and changing the aluminum plates. Okay, the aluminum plates are loaded onto the telescope like a cartridge is loaded onto a printer. Okay, so these cartridges of aluminum plates are loaded before every night's observation, and that's what you will be seeing in this video. Okay, it's a time-lapse video. So here you can see the aluminum plates being taken on a trolley. And that's the back end of the telescope where all the instruments are present. So the dome is a retractable dome. So the dome is removed from it. Now the telescope is ready for observation. So every night, as the Slow and Digital Sky Survey or as the Apache Point Observatory gets ready to execute the survey, this kind of a routine is performed, okay, where somebody manually loads the cartridge, and the cartridge contains aluminum plate with holes punctured in it. Okay. And the fun doesn't, so this is what a typical image taken using the Apache Point Observatory would look like. So this is a photograph of a certain patch of the sky taken by the Slow and Digital Sky Survey. And you can see that some of these spiky things, okay, these are stars, and some of the other objects, many of the other objects in this particular image, they are galaxies. Okay? They are galaxies outside of the Milky Way. So by looking at an image like this, they've identified the objects for which they need to record the spectrum. So usually they choose objects above a certain brightness level. Okay? They don't go for very faint objects, because whatever looks very faint in an image, when you actually record a spectrum, the signal to noise of the spectrum will be very, very low, because you are spreading the light. Okay? Here you are lumping the light, all the light into a few pixels. Once you record a spectrum, that little bit of light gets spread over a larger area. So you're going to get a very low signal to noise spectrum in the given exposure time. So usually they apply a brightness cutoff, and any object that is brighter than that, which looks like a galaxy, they identify its location in that patch of the sky. And here is an aluminum plate, okay, and it's coated with some material, and you can see that they have circled certain holes with a pen. Okay, and those are the holes in which optical fibers are going to be connected. So many of these aluminum plates are reusable, because even if it has holes, many holes in it, only the ones in which you connect an optical fiber will take the light and will give the spectrum. Okay, so you don't waste an aluminum plate just because it has been used once. Okay, it is reusable. So you can see that there are the holes in which optical fibers should be connected. They are all marked here using a pen. And then somebody manually connects optical fibers to all these holes. Okay, so I'll show you a video of this. So all these blue and red cables are optical fibers, and they are being manually connected to all the individual holes. So this process happens, and then the light is fed to a spectrograph, and the spectrograph renders the spectrum, and the spectrum is later. So in one shot, you get about 100 to thousands of galaxy spectra, and these spectra are analyzed carefully. And once you analyze the spectrum, you will know how much the spectrum is exhibiting a redshift, and using that, you can determine the redshift of that galaxy. So you know the coordinates of the galaxy in the sky. You also know the redshift, which is a proxy for distance. So the SDSS did this for a long period of time. The survey started in 2000, and it kind of formally ended in 2008. Although even now, the SDSS survey is going on in its new incarnation. So several years of data taking happened, and several episodes of data release also happened. And at the end of this entire survey business, SDSS was able to produce a map like what you're going to see now. So this is an animation, this is a visualization of the 3D map of the universe that SDSS produced. And in this animation, what you're going to see are objects that are going to fly past us, and each object that flies past us is a galaxy that SDSS identified in the sky, and for which the redshift measurement was done, okay, by recording the spectrum. And in the center of this image or this animation is Milky Way. So sitting here in Milky Way, we are looking at one quarter of the sky and measuring the distances and positions to galaxies. Sorry. I'll just pause it at a convenient location. So I'll just freeze it here. So this point is where the Milky Way is, and these two slices, they correspond to the regions of the sky that the SDSS observed, and these black regions are regions which the Slow and Digital Sky Survey could not observe. So that's why there are no data points there, and hence they are black. And the important thing here is that it's every pixel that forms this image corresponds to the location of a galaxy in our universe. Okay? So this entire map that you're seeing is made of tiny dots, as we saw earlier. If I were to rewind back, okay, you can see that each one of them corresponds to a galaxy. And so this represents how galaxies are distributed at large physical scales. Okay, and so this is how it is. And what this shows is that the galaxies are not distributed uniformly. There are some regions where there are no galaxies, and there are some regions where galaxies are significantly clustered together. So these regions which are devoid of galaxies, they are generally referred to as voids, and the regions where there are large number of galaxies present in a tiny volume of space, tiny in speaking astronomically, okay, so in a volume of space, these are generally galaxy groups, and more importantly, galaxy clusters. So this is the hierarchy of structure, or this is the architecture of our universe, and astronomers have a name for it. They call this the cosmic web. Okay. So here's an image of whatever you just saw. We are located We are located at the tip of this pie chart, and you can see here this is right ascension that is plotted, and this is redshift converted into distance in terms of billions of light years. And each dot that you see here is the location of a galaxy. And so the bottom line of the story is that on megaparsec scales, the matter distribution of the universe is not uniform, but it forms an intricate pattern of voids and clusters and groups of galaxies. And this is what is called the cosmic web. So the analogy is obviously from the web-like structures that we see in the natural world. So just to summarize the story so far, the galaxies in our universe are not distributed uniformly or randomly. Their distribution has a pattern that is web-like. So I've just highlighted these two words here, uniformly and randomly. And what I mean by that is a uniform distribution of galaxies would have looked like this. You can imagine this in 3D space. Okay, here I have drawn it in 2D space, how a uniform distribution would look. Any direction you look, you are going to encounter the same number of galaxies. Okay. That's what a uniform distribution would look like. Now, if the distribution was totally random, then it would look something like that. But surveys like the Sloan Digital Sky Survey, the 6-degree field survey, the 2-degree field survey, Galaxy Redshift survey, all these surveys, they all time and again tell us that the distribution is neither uniform nor random, but it's more like a filamentary structure, a web-like pattern, which astronomers refer to as the cosmic web. So these filaments of the web, where they join, those are the really overdense regions of our universe, and that's where you encounter a large number of galaxies, and that's what typically we identify as a galaxy cluster. Connecting these galaxy clusters, which forms the nodes of these filaments, are sometimes strings of galaxies, but there is also a large amount of diffuse gas that is present in these filaments that connect the nodes. So that's intergalactic medium that's present in those regions. Okay. So uniform distribution, random distribution, web-like distribution. So now the question is, how did the cosmic web-like structure come into existence? We know that the early universe conditions were nearly uniform. So from a nearly uniform early universe conditions, how did this clustering of matter happen? And that is the story of the formation of large-scale structure in our universe. There is a lot of theoretical work that has happened to understand, to simulate using supercomputers the formation of large-scale structures under the influence of gravity. Okay? So how did this peculiar web-like structure come into existence? And when we are talking about the structure of the universe at such large physical scales, then the only force that we need to primarily be concerned about is the force of gravity. So the evolution of the universe at large scale is governed by or is ruled by gravity. And there are some ideas on how this large scale structure would have come about, but I will confine myself to observational ideas, okay, ideas that are seeded by observations. And I won't go too much into theoretical ideas which are still being tested using observations. Okay. So this is I'm sure, since most of you are astronomy enthusiasts, I'm sure you know what it is. This is the cosmic microwave background radiation, an all-sky map of the cosmic microwave background radiation. CMB, or the cosmic microwave background radiation, are the oldest photons that we can observe in the universe. Okay. Cosmic microwave background comes to us from a time that is roughly 300,000 years after the Big Bang. In astronomy, in cosmology, that epoch is referred to as the surface of last scattering. That is the time when the photons, the radiation in our universe, underwent their kind of last scattering with matter. Okay. In other words, the mean free path of the photons after that time period, 300,000 years after the Big Bang, after that time period, became sufficiently large that they could free stream through the universe without interacting with matter. But these photons were free streaming through a universe that was expanding, okay, and it's an adiabatic expansion, which means that the energy required for the expansion of the universe has to come from the internal energy of the universe. So the photons lost their energy, okay, and which means the radiation cooled down. And today, in the present universe, the relic radiations from the Big Bang, we observe at microwave wavelengths. The intensity of that background peaks at microwave wavelengths corresponding to a temperature of roughly 3 Kelvin, that is 3 degrees above absolute zero. And so this, what you're looking at here, is an intensity map of that cosmic microwave background radiation, which is coming to us from all directions. Okay, so it is omnipresent. There is no place in this universe where cosmic microwave CMB photons are not present. And there have been a lot of dedicated there have been several measurements of the CMB, both using ground-based facilities, balloon experiments, and also using space-based satellites. The 3 famous space-based satellites that have mapped the cosmic microwave background radiation are the COBE mission, the WMAP mission, and the Planck mission. This particular one map that I'm showing is from WMAP, which is Wilkinson Microwave Anisotropy Probe. And what you're looking at here, as I mentioned, is an all map, and it's an 8-off projection. Like in geography, how you show Earth using an 8-off projection. Similarly, the entire sky, the celestial sphere, is shown as an 8-off map. And here you can see some colors. The colors represent the intensity of the CMB photons that are reaching us from that patch of the sky. Okay, the blue regions correspond to regions that are slightly cooler than 3 Kelvin, and the red correspond to regions that are slightly hotter than 3 Kelvin. The temperature difference is only very, very small, and 3 Kelvin is kind of the average temperature of the black body radiation, which is the CMB, cosmic microwave background radiation. So these are called hot spots, and the blue ones are called cold spots. And why the CMB? Why am I talking about the CMB? Because the CMB is the earliest picture of our universe coming to us from electromagnetic radiation. Okay. Now we have gravitational wave astronomy, which can even provide us information from time periods earlier to the CMB. But if you are focusing on electromagnetic radiation, then this is the farthest that we can see in terms of electromagnetic radiation. And it is giving us a picture of the state of the universe when the universe was just 300,000 years after the Big Bang, okay, after the origin. And so you are looking at a map of how the universe was 300,000 years after the Big Bang. And the hot and cold spots, they are telling us that the universe was did not have a uniform density distribution at the time of last scattering, at the surface of last scattering. There were some regions which had densities that were higher than average, and there were some regions which had densities which were lower than the average. Okay, so there were over-density regions, and there were under-density regions. And those over-density regions and under-density regions, when I say over-density and under-density, I'm talking about matter density. Okay? Those over-density and under-density regions are what we see when we are looking at the map of radiation that is coming to us from that time period, because just before the surface of last scattering, matter and radiation were coupled together. So whatever matter was doing, radiation was also participating in it, and therefore the anisotropy in the cosmic microwave background radiation is telling us that there was anisotropy in the distribution of matter at those early epochs. So there were density enhancements and there were underdense regions, and it is this information that we get from the CMB which is used to understand the formation of large-scale structures in the universe. This is what is used to understand how did all the unique objects in the universe originate from the nearly uniform conditions of the early universe. Okay? These tiny density enhancements got amplified over time, over 13 billion years that have elapsed since the surface of last scattering. These tiny density enhancements have been amplified by gravity, creating galaxy clusters, galaxies, etc. that we see in the present universe. So that is why after the detection of the cosmic microwave background radiation, astronomers were hell-bent on finding this anisotropy, because without this anisotropy, you don't have any where to start this modeling of how the large-scale structure of the universe came into existence. Okay. So I'm going to show this is largely done in the domain of supercomputing, and I'm going to show you results from one such numerical simulation of the formation of large-scale structure in our universe. So what astronomers do is they take a representative volume of the universe. So here you see a cube. This cube has a certain dimension. Maybe it extends several megaparsec. So you're not looking at a tiny volume. You're looking at an astronomically large volume. And the blue represents the distribution of matter in the very early universe. Okay? The number on top here is redshift. Higher the redshift, the further back in time we are talking about. So redshift of 30 means that's something that we cannot really observe. Okay, so this corresponds to the very early universe, and the distribution of matter is shown here in blue. And what in these simulations, what they do is they add tiny density perturbations to this distribution of matter. And these density perturbations are inspired by the anisotropy that is seen in the CMB. Because the CMB anisotropy says that the matter density was not uniform in the early universe. So inspired by this observational evidence, tiny density inhomogeneities are added into this distribution of matter. And from that point onwards, they let the simulation run with gravity as the only force that is acting between these matter particles which are present in the simulation. Okay. So from that point onward, they don't interfere in any way. They just allow the universe to evolve within this box under the influence of gravity. So we'll just see what one of these simulations looks like. As the simulation runs, you will see the redshift value decreasing, and that is to represent the passage of time. Okay. So here you go. And they have paused this particular animation at a redshift that is 0.4, which is very close to the present redshift, which is redshift of 0. And you can see that matter has self-assembled itself into these filamentary structures where the nodes of the filaments have a large density of matter present, and the filaments connect these nodes. Okay. And this is exactly what these galaxy redshift surveys also see. So if you look at the SDSS galaxy distribution map or any of the other large-scale galaxy distribution maps, we find the exact same thing. So starting from those primordial density fluctuations, these simulations are able to reproduce the observed three-dimensional architecture of our universe. Now I have skipped many things here. For example, what you just now witnessed is the self-assembly of dark matter, not baryonic matter. Okay, not matter that is made of protons or neutrons, but dark matter. And so there are some layers of detail which I am skipping for now. But in the Q&A, if you have any questions, maybe we can talk about it then. Okay. So this whatever I have covered till now is only a very superficial, a peripheral overview of the formation of large-scale structure and the observational efforts that have gone into mapping the three-dimensional geometry of our universe. If you want to read more into this, a really interesting accessible book is this book written by Richard Gott, who is one of the pioneers of this large-scale structure model of our universe. And this book came out, I think, in 2016 or so. It is written at a popular science level, so anyone can easily read through this. So it gives a fairly comprehensive historical and scientific overview of this topic of large-scale structure of the universe. Okay. So I have about maybe 5 minutes or 10 minutes more time. So what I will do is I'll just quickly go through this question of, is this cosmic web static or is it evolving? In other words, what I'm going to talk about is the expansion of the universe. Okay, this is also a very interesting topic. Now, many of you may have read on your own or may have taken courses where you would have studied the expansion of the universe. So most of what I'm going to talk about may be redundant information, but I'll just go through it anyway for those who have never encountered this before. Okay, so the fact that we are living in an expanding universe, that realization came to us in the early 1900s. Okay, so the beginning of the 20th century, and incredible as it may seem, the knowledge that there are galaxies beyond the Milky Way, that also came to us only in the beginning of the 20th century. Okay. Prior to 1900s, astronomers did not even know that there were galaxies external to the Milky Way. So extragalactic astronomy is only 120 years old, and in the beginning of the 20th century, in early 1900s, Edwin Hubble and assisted by a person called Milton Humanson, they used the 100-inch Mount Wilson telescope. So Mount Wilson Observatory was the largest ground-based observatory in the early part of the 20th century. This Mount Wilson is a location in the US. The telescope is located at an altitude of about 5,000 feet above sea level. So it's a mountaintop observatory, and 100-inch roughly corresponds to half meter, I think. Okay, so it's a half a meter telescope, and this half a meter primary mirror diameter telescope was the largest ground-based observatory that was available to astronomers back in those days. So using this 100-inch Mount Wilson telescope, Edwin Hubble and Milton Humanson, they carried out a series of observations which became path-breaking. Okay. So what they did is they selected about 24 galaxies which were known to astronomers. Now remember that just few years before, astronomers realized that what they were looking at were galaxies outside of the Milky Way. Okay. And Hubble also played a role in that. But extragalactic astronomy had just born, and within a few years, these kind of galaxy measurements had started. So they looked at about 24 galaxies in the local universe. They recorded the spectrum of all those 24 galaxies. Okay? So back in those days, it was using photographic plates. There were no CCD cameras, etc. So they did that, and I'll just show you a picture of a video of this 100-inch Mount Wilson observatory as it is now. So this is that particular telescope that Hubble and Humanson used. Milton Humanson was the night sky assistant who helped Hubble carry out these observations. So quickly, here is an image of galaxy just to help us understand what a galaxy looks like in a picture and what a galaxy looks like in a spectrum. I have shown this. This is a galaxy as seen in an image, and this is the spectrum of that galaxy. Okay. So you have the flux along the y-axis and the observed wavelength along the horizontal axis. So that's what a spectrum would look like. And you can see that there are absorption lines and there are also emission lines. And if you can identify what these absorption lines and emission lines are, for example, here it's marked H alpha. H alpha means Balmer alpha. H beta means Balmer beta. So NA means sodium D1, D2 lines. Okay, these are the ionized calcium triplet lines. So if you can identify the nature of these absorption lines, then you can measure whether there is any redshift or blue shift for this galaxy. Because in laboratory, we know where these lines should occur. Okay? For example, the H alpha line should occur at 6563 angstrom. Now here you can see that the line is not occurring at 6563 angstrom. It's occurring very close to 7000 angstrom. So what that means is that the spectrum is redshifted. So by identifying these lines and by identifying where these lines fall in the observed spectrum, astronomers can measure the redshift of these galaxies. And once you measure the observed wavelength of lines, and if you know the rest of those lines, the laboratory wavelengths of those lines, then we can calculate what is the velocity along our line of sight of that galaxy relative to us. That is the radial velocity of that galaxy relative to us. Okay, using this expression. So if the H alpha line, that is the Balmer alpha line, occurs at 7000 angstrom, then you would put 7000 here. And we know that in laboratory, that line is supposed to be at 6563 angstrom. You will put that there and you get the velocity of that. Now, since the galaxy can have only one velocity, all the absorption lines will have the same ratio of lambda observed to lambda rest for that particular galaxy. Okay? So whether you take the calcium line or the sodium line or the H-alpha line or the H-beta line, for a given galaxy, this ratio would be constant, which means that the galaxy has a single velocity, radial velocity relative to us. Okay. So Hubble and Humanson, they looked at this half a dozen, others 24 galaxies in the local universe, and they recorded the spectrum, and they found out that vast majority of these galaxies were exhibiting a systematic redshift in their spectrum, which means that they all are receding away from us. So if we are this green galaxy, then Hubble and Humanson's observation showed that these galaxies are all moving away from us. Okay. Now, so this led to the idea that we are not living in a static universe. Our universe is dynamic, it is expanding. So what they did is they measured the radial velocity from the spectrum, and they also independently measured the distances to these galaxies, okay, using Cepheid variables. I'm not going into the details of it, but if anybody is interested during the Q&A, I can address it. So they measured the redshifts to all these galaxies as accurately as possible. And from the spectra, they also measured the radial velocity. And then they produced a plot like this. So here, each blue data point corresponds to the radial velocity and the distance of a galaxy from us. So each blue data point corresponds to a galaxy. And if you count the number of data points here, it will come to roughly 24. Okay, so there were 24 galaxies that they looked at, and they found out that it looks like a scatter plot, except that you can see that there is a positive correlation between distance and radial velocity. The farther away a galaxy is, the faster it seems to be receding from us. Okay. Galaxy that's at 2 megaparsec distance from us seems to be moving with a greater velocity relative to us, which means that the spectral lines are shifted more in that. And a galaxy compared to a galaxy that is at 1 megaparsec distance, which seems to have a lower recession velocity relative to us. The spectral lines will be less redshifted in that. So this led to this famous expression, which we now refer to as the Hubble redshift recession velocity relationship. Radial velocity is proportional to the distance of the galaxy from us. V is equal to the Hubble constant. We now refer to as the Hubble constant times the distance. Okay, you can establish what that constant is by fitting a regression line to this scatter plot. So the lesson that we learned from Hubble, Humanson, and subsequent observations is that most of the galaxies are receding away from the Milky Way. The farther away a galaxy, the faster is its recession speed. But now comes the interesting part. Okay, if all the galaxies are moving away from us, then the immediate conclusion that one may arrive at is that we are the center of this expansion, because everything else is moving away from us. But astronomers of that time period, they did not make that mistake, because there is no reason why Milky Way should be the center of the universe. So what they did is they, so if all the galaxies are moving away from the Milky Way, then the question is, are we the center of this expansion? In other words, are we the center of the universe? Okay. So this is what Hubble and Humanson observed. They found that all the galaxies are moving away from us. But the interpretation that was given for these observations is that no matter which galaxy we live in, we will observe the same. In other words, if you are living in this, if you are astronomers living in this red galaxy, and if you were to do a similar observations that Hubble and Humanson did, we will find all other galaxies moving away from us. If we were astronomers living in this blue galaxy, and if we were to do the same set of measurements that Hubble did, then again we will find all other galaxies moving away from us. Okay. So just as a help you understand this, I'll just show you a small way to do this. Okay. So I don't know whether you guys can see this screen. You're able to see this, right?
Yes, it's visible.
Yeah. So here is that picture that I showed, and let's say that we are living in the green galaxy. Then, and we are measuring the spectrum of all the nearby galaxies. So then what we would find is that all the galaxies are receding away from us, which means after some significantly large period of time, the red galaxy would have moved away from us, the blue galaxy would have moved away from us, the black galaxy would have also moved away from us. Okay. This is what we would observe. And the closer the galaxy is, the less it would have moved away. The farther the galaxy is, the more it would have moved away from us. Now, if we were not in this green galaxy, let's say that we were astronomers in this red galaxy, if we were to carry out the same observations, then we would find that the green galaxy is moving away from us, the blue is moving away, the black is moving away from us. Now, if we were not living in the green or red, but if we were living in this blue galaxy over here, again, we would observe the same thing. So this is just a low-level animation to convey that point. And the reason why I'm able to show this in this kind of manner is because there are two slides here. And in one of the slides, I have increased the distances between all the galaxies. So this is exactly how astronomers understand the expansion of the universe. Okay, so if you think of the universe as a grid, okay, there are two ways in which the redshift can be explained. One is, let's say this galaxy is positioned at this particular point in the grid and this galaxy is positioned at this particular point in the grid. There can be a redshift if the galaxies are moving within this grid. Okay, this is one way for redshift to happen. But the problem with this is that there will be equal number of blue shifts and red shifts if this were to happen, because as this red galaxy moves away, there could be a blue galaxy which will be coming in this direction if all galaxies are moving randomly. Okay, but we don't see that. Instead, what is happening is, imagine the red galaxy being at this point and the black galaxy being at this point. Instead, what is happening is this fabric of space itself is expanding, so that after a long period of time, the physical separation between any two nodes, the physical distance, has increased. So in other words, space is what is expanding, and it is not galaxies that are moving around in this space. Okay, so galaxies are remaining where they are, and the space between those galaxies is stretching. So this is the way in which this cosmological redshift is interpreted. Okay, you have the fabric of space, and the space itself is expanding with time, and that expansion results in the redshifting of photons which are traveling from these galaxies to other galaxies. So suppose a photon starts its journey from this galaxy, and on its journey towards this galaxy, at every instant, the photon is traveling through space that is slowly expanding. So instantaneously, there is redshift happening to that photon, and all that cumulative redshift will result in a significant redshift when that photon gets detected by an astronomer in this galaxy. And when you convert that redshift into velocity, okay, you are making a mistake, because the redshift is not because of the kinematics, the relative velocity between this galaxy and that. It is because of the expansion of space happening between these two. So the universe does not have any center. The expansion is happening everywhere, and that's the correct way to think about the expansion of this cosmic web. And the reason why it is wrong to interpret cosmological redshift in terms of velocity is conveyed in this plot. Okay, so what is plotted here is the velocity of galaxy divided by velocity of light. That is this v by c term. That is what is plotted along the y-axis here, v by c, which means, so 1 means v is equal to c, and 0 means it's not moving. There is no radial velocity. And along the x-axis is this term in the left-hand side, lambda observed by lambda rest. So you can see that when the observed wavelength is a few times the rest wavelength, the velocity of the galaxy becomes very close to the speed of light, 60%, 70%, 80% the speed of light. Okay. Now, how can a galaxy with billions of stars in it, how can it acquire such large velocities? The energetics won't allow it. Okay. So, which is why it's wrong to think of redshift, observed wavelength, being greater than rest wavelength, which is what redshift is. It is wrong to think of redshift of these distant galaxies as due to recession of those galaxies. It's not because of those galaxies actually moving. It is because of the space between us and that galaxy slowly expanding as the photon travels through this expanding space. So the redshift we measure for galaxies is not a measure of velocities of those galaxies. The redshift comes from the expansion of space. Rather than galaxies flying away from each other with large speeds, it is a space between galaxies that's uniformly growing, and that's the correct way to think about expansion. And for that reason, in cosmology, the redshift is usually prefixed with a word called cosmological redshift, differentiated from kinematic Doppler shift. Okay? So cosmological redshift is different from kinematic Doppler shift. In the spectrum, both manifest in the same way as a shift in spectral line, but depending on the value you get for the redshift, you have to give it a different interpretation. In this case, you have to interpret it as the expansion of space itself. Now, how much time I have? Can I take 5 minutes?
Yes, sir. Sure. No problem.
Yeah, so I'll just try to go as fast as possible. So this Hubble constant, as it turns out, is a it's not just any proportionality constant. Okay, VR is proportional to D and VR is equal to Hubble constant into D. So it's not just any proportionality constant. Over the last 100 years, astronomers have been trying to measure the Hubble constant as accurately as possible. For example, in the days of Edwin Hubble and Milton Humanson, the value of Hubble constant that they measured was 500 kilometer per second per megaparsec. Now, Hubble constant has these weird units, okay, kilometer per second per megaparsec. And there's a reason why the Hubble constant is written in these units. If you look at it, kilometer is unit of distance, megaparsec is also unit of distance. So ideally, dimensionally, these two cancel off, and Hubble constant just has dimension of 1 by second, inverse time. Okay. But the reason why it's written this way is because it helps us to easily understand what that constant is saying. For example, if you say that h0 is 500 kilometer per second per megaparsec, what that Hubble constant value is saying is that if there is a galaxy that is at 1 megaparsec distance from us, it will be receding from us with a speed of 500 kilometers per second. If there is a galaxy at 2 megaparsec distance, it will be receding away from us with a speed of 1000 kilometers per second, so on and so forth. So writing it in this unit helps us to quickly come to that conclusion. Okay. So in 1927, the value that people measured had this kind of a numerical value. 1950s, the measurements improved and the value came down to 200. 1970s, this was the value of Hubble's constant. 2001, using the Hubble Space Telescope, there was a very prestigious project called the Hubble HST Key project, and that they measured a value of 72 kilometers per second. 2012, WMAP measurements gave a value of 69 kilometers per second. And 2018, Planck measurements gave a value of 68. So the value is now more or less stabilized to 70 kilometers per second per megaparsec. Now, one word of caution which I want to add here is, from 1927 to 2020, the value has decreased. That is not because the Hubble constant has actually decreased. It is because our measurements have become better. Okay. Back in those days, in 1920s, there were large uncertainties in distances to galaxies that were estimated because they were using very crude techniques. Okay. So those uncertainties resulted in very wrong values for the Hubble constant. So this is not the Hubble constant itself evolving. This is our measurements getting better and better, and now the value is around 70 kilometers per second per megaparsec. And this measurement is very, very important. Okay, and to help you understand why this measurement is important, what is the significance of this Hubble's constant, I'll just give a very simple analogy. It's a very, very simple analogy. So imagine that there is a race between two cars. Okay, and let's say that you missed the starting of the race. Okay, so you don't know when the race started. Okay, you come to the podium or you come to the venue after the race has started, and when you enter, come in, you find that the race has already started, and you find that the green car is moving with a constant velocity of 40 kilometers per hour. Let's say that you have a magical instrument which will give you the instantaneous velocity, and the red car is moving with a speed of 20 kilometers per hour. And at that exact instant, let's say that you have an instrument that tells you how far away they are from the starting line. You find out that the green car is about 80 kilometers from the starting line and the red car is about 40 kilometers from the starting line. Now, if I were to ask you when did this race begin, it's very easy to calculate. Okay, so 40 kilometers per hour speed, 80 kilometers, you will say that this race started 2 hours before. And the same here, 20 kilometers per hour, 40 kilometer distance covered, so 2 hours before. Okay. But in saying that, we make a very crucial assumption, which is that the velocities that we are measuring for this car has been a constant throughout this journey. Okay. So you'll keep that in mind. And the reason why this is important is because we can apply the same logic to the Hubble distance velocity diagram. Sitting here on Milky Way, we are measuring distances to galaxies and we are measuring how fast they are moving. Okay. So now we can rewind back this entire scenario and ask, when did this race begin? When did this expansion begin? When did this expansion of our universe begin? Okay. So, in other words, if our universe had an origin, then when was that origin? How far back in time?
Sir, your voice is cut. Guys, don't leave yet. He'll be back. It's probably an internet issue.
Sorry, I lost my connection in between. I don't know how much you heard. Did I lose you at the last slide or?
Sir, you left off at the part where you were talking about the universe expanding.
Okay, so I lost you quite a bit. So you
could go to the slides. I'll show you there where it.
Yeah, right. That's the best way to do it. Yes. So sorry, I didn't realize that I had lost connection.
Yes, sir. It's no problem. It's fine.
Did you see this particular slide?
No, not this one.
Oh my God. Okay, I lost you a lot. Okay. So this part, correct way to think about the expansion?
Yeah, this is done. Yeah. The flying with each other, yeah, that's done. Yeah.
This is done. And what about this?
Okay, I think the slide didn't appear, but then you explained about this, saying that the measurements got better with time.
Okay, yeah. So
yeah.
I was just showing how the measurement of the Hubble's constant has evolved over time, and I was just trying to caution that this change in value of Hubble parameter, Hubble constant, was not because the Hubble constant itself was changing. It is because our measurements were getting better and better. So in early days, the measurements were very crude, so that resulted in very rough estimates of the Hubble's constant, which were wrong. And more recent measurements give us the accurate value of the rate of expansion of the universe. So the Hubble constant, the current value is stabilized somewhere around 70 kilometer per second per megaparsec. Okay, so this is the value. And as I was also mentioning that the reason why the Hubble constant is written in these kind of units, kilometer per second per megaparsec, is because if you look at it, kilometer and megaparsec are both distance units, so they cancel off. And in reality, this Hubble parameter is inverse time. But the reason why it's written with these weird units is because this gives us an intuitive sense of the rate of expansion of the universe. For example, if I say that the universe is expanding with 70 kilometer per second per megaparsec, what it means is that if there is a galaxy that is at 1 megaparsec distance from us, then it will be moving away from us with a speed of 70 kilometer per second. If there's a galaxy at 2 megaparsec, it will be moving with a speed of 140 kilometer per second, so on and so forth. Okay, so now this Hubble, the reason, so for close to 100 years, astronomers have been trying to measure this Hubble constant as accurately as possible, which means that there has to be something very important about this Hubble's constant. It cannot be just any proportionality constant. And as it turns out, Hubble's constant is a very, very important parameter to measure. And to understand that, the best way to understand that is with the help of this simple example. Okay, so imagine that there is a race between two cars, a green car and a red car. And let's say that we arrive at the venue of this race quite late. Okay, so we arrive late, and the race has already started. And when we arrive at the venue, we find that the cars are already moved away from the starting line. So let's say that with a device, we measure the velocity of the green car, and we find that it's moving with a speed of 40 kilometer per hour. And we measure the instantaneous velocity of the red car, and we find that it's moving with a speed of 20 kilometer per hour. Okay, so these speeds are not quite representative of what we would call a race, but let's just assume that these are the values, and say that we also measure at that instant how far away these cars are from the start.
So sorry guys, just wait for a while. He'll join back for the question and answer session.
Yeah, sorry.
Yeah, you were talking about the green and red car. Like you were halfway through.
Right. I'll just quickly finish that. Sorry about this internet connectivity. It's beyond me. I don't know why. Just a second.
Yes, sure.
Yeah, so I was just saying that you can apply the same analogy of when that race began in the context of these galaxies. Okay, these galaxies are receding away from us, and we can ask this question: when did this race begin for these galaxies? In other words, when did the expansion begin? Okay, so in other words, when was there ever a time when these galaxies were all close to each other, which corresponds to the origin of the universe? So how far back in time was that origin of the universe, and for how long this expansion has been happening? So what that means is we are asking about the age of the universe, how old the universe is. Now, we cannot give any special consideration to any of these data points because they are all equally valid measurements. So what we have to do is we have to fit a regression line and measure the slope of it, which will be the Hubble's constant, and the inverse of that Hubble's constant will give us the age of the universe. Okay, so that's why the Hubble constant is a very, very important parameter to measure. An accurate estimate of the Hubble's constant will give us an accurate estimate for the age of the universe. So if you adopt a value of about 70 km per second per megaparsec, which seems to be the consensus value these days, you will get an age of the universe that's roughly 14 billion years, which corresponds to the age of the universe that we estimate from other sources also. Okay, so the Hubble constant is not just any other constant; it's very, very important, and that's why a lot of observational effort has gone into determining the Hubble constant as accurately as possible. So just to summarize, what I was trying to tell in this entire presentation is that the universe that we are living in, there is evidence that we are living in an expanding universe, and there is no preferred center for this expansion. This expansion is happening everywhere. The expansion indicates that the universe could have had an origin, because if you rewind this expansion backwards, there must have been a time when everything was closer together. By measuring the rate of expansion of the universe, the rate of expansion of the universe is given by the Hubble's constant. By measuring the rate of expansion, one can get an estimate for the age of the universe. And lastly, with the topic that we started off with, which is that galaxy redshift surveys like the Sloan Digital Sky Survey has convincingly showed what the three-dimensional geometry of our universe is like. Our universe, the matter in our universe is distributed neither randomly nor uniformly, but it is distributed in a kind of filamentary cosmic web-like structure. So all theories of structure formation, okay, whatever theories of structure formation that theorists may mount, they have to reproduce this large-scale structure that observations are showing. Okay, so with that, I will stop the presentation and I'll be happy to take questions.
Yes, sir. I have a question about the punching holes in the aluminium foil part.
Yeah.
So when you do that, see already there are the measurements which we measure are like very approximate, right, with a lot of error bars and stuff. So doing this will increase the error even further, right? So would this lead to major problems? I'm assuming all the other sky surveys also do similar methods. So
yeah, so the sky surveys all adopt this multi-object spectroscopy technique. So there are some edge effects, okay, because of imperfections in the way the holes are punctured. There are some edge effects that happen, but most of the light that comes in the center of that hole is enough to produce a fairly good signal-to-noise spectrum of these bright galaxies. So that systematic uncertainty because of the problem with the holes in the aluminum foil is not going to significantly affect the measurements. But you are right, light that is coming from the periphery of those holes are affected by how well the hole is punctured. So there are some edge effects to that, but it doesn't affect the measurements in any significant way.
Okay, sir, thank you. So there's one more question in the chat box. Aishwarya asked, what's the universe expanding into?
Yeah, so the universe is not expanding into anything. Okay, as I mentioned, the expansion of the universe is an expansion of space. So which means that there is nothing outside of the universe that it can expand into. Okay, space is being created as the universe is expanding. Okay, so it is a self-contained system. Okay, that's the only way to understand it. So you cannot draw a boundary to this universe and say that this is the universe and this is outside of it, because whatever we call as the universe includes not just the matter and the dark matter and the dark energy that we talk about. It also includes space and time. So wherever you draw a physical boundary, what is outside of it is also part of the universe. So the universe is not expanding into anything. So I see some questions in the chat box. Shall I just go ahead and answer them? Or?
Yes, sir, sure. Yeah.
Yeah. So Harry is asking, is the rate of expansion of universe constant or is it increasing or decreasing? So the current measurements show that the universe is not just expanding, but there is an increase in that rate of expansion. And in fact, measurements also show that there is an increase in the rate of expansion, which means that there is a jerk it's called the cosmic jerk, okay, in the rate of expansion of the universe. So the universe seems to be expanding at ever greater rate. And the reason, so this is actually counterintuitive, because if you think of Big Bang as an impulse force, okay, I'm simplifying things a lot here. Okay, so if you take a proper cosmology course, this kind of an argument would not go. But I was just saying, for the sake of the 1 minute that I have, let's assume that Big Bang is an impulse force, like kicking a football. Okay, so you start off the expansion, and then matter is present within this expanding universe, and gravity is a persistent force. So gravity will always try to slow down this expansion. So eventually, if there is enough matter present in the universe, we will expect this expansion to slow down and stop, and maybe contract if there is enough. The universe will start contracting under the influence of gravity if there is enough gravitating matter in the universe. Otherwise, the expansion may go on slowing down at an ever increasing rate, but never stopping. Okay, so these are two possible world models. One is called a flat universe, and the other is called a closed universe. But the current observations show that the expansion of the universe is not slowing down. In fact, it is speeding up. And the reason for that is dark energy. Okay, so we are living in the present. We are living in a universe where the energy density is dominated by a mysterious component which is called dark energy. Nobody has any idea what dark energy is. There are some interesting speculations, its hypothesis or educated guesses on what dark energy could be, but there is no exact understanding of what dark energy is, except that there is multiple lines of evidences that seem to show that only if you invoke this dark energy component will we be able to explain some of the observations that we some of the observational things that we see. Okay, so this dark energy is a kind of negative pressure. It's a kind of repulsive force which is causing the rate of expansion of the universe to increase with time. And as I mentioned, currently we are living in a dark energy dominated universe. What that means is that if you take a representative volume of the universe, when I say representative volume of the universe, I don't mean a volume of the universe in the room that we are sitting. The Earth is a very artificial environment. Okay, the universe is not like the Earth. The universe is a very, very diffuse place. And so if you take a representative volume of the universe far away from galaxies, etc., and measure the energy density, so matter density converted into energy density, if you measure the energy density in that volume of space, you will find that baryons or ordinary matter possess only 4% of the total energy density within that volume. Dark matter occupies about 25%, so that's 30% altogether, and the remaining 70% is occupied by something called dark energy. And so that is the basis of the statement that in the present universe, the universe that we are living in, is dark energy dominated. Okay? And this dark energy is causing the expansion of the universe. Okay, so that was a very long answer. So Ashwati is asking, how do we differentiate the spectrum of a galaxy from that of a star? Okay, so Ashwati, this spectrum of galaxy typically contain many emission lines, and stellar spectra usually don't have emission lines, and the spectrum of an individual star will resemble that of a black body. Okay, so it will have a Planck function-like curve, whereas the spectrum of a galaxy will be the composite of light from billions of galaxies in billions of stars in that galaxy, and also gas, that is interstellar gas, that is glowing within that galaxy. So the overall energy distribution of the light from a galaxy is different from the energy distribution of light from a star. Energy distribution, what I mean by energy distribution is how energy is distributed as a function of wavelength. That is different for galaxies and different for stars. So the spectrum can easily help us differentiate between whether we are looking at a galaxy or a star. So Saurabh is asking, there is a cosmic web map. Can you tell how much time was required to make this map? So I can tell about the Sloan Digital Sky Survey. The survey lasted about 8 years, but during that 8 years, in between, they were releasing data. Okay, partially they were releasing data that was getting completed. So I think a couple of years is what it took them to generate a map like the kind of map that we saw. Okay. So these are long and hard observations. They cannot do it over 1 or 2 or few nights. If the universe is expanding and the galaxies themselves are not moving, how do we observe the redshift? Okay, so I think I tried to explain that part in my presentation. So the space, let's say that you have a galaxy that's emitting light. The photons are traveling through space. Now the space itself is expanding. The fabric of space itself is stretching, which means the photon is traveling through expanding space. Okay, and during this expanding journey through this expanding space, at every instant the photon is losing a little bit of its energy. And that losing a little bit of energy means the photon is getting redshifted. So the incremental losing of energy as the photon travels through this large distances, so that separates us from distant galaxies, cumulatively it will result in a substantial amount of redshift when we detect that photon here on Earth. So there is a YouTube question, how is the size of the hole and the type of metal used is determined? So the size of the hole is basically a pinhole. I don't know exactly whether there is any thought process that has gone into determining the size of these holes. The optical fibers have to fit into those holes, and enough light should be coming in through those holes when we position those holes and look at the galaxies in that patch of the sky. Okay, so but beyond that, I don't know the technical details of how the sizes of those holes were estimated. I think, Arjun, that's all I see by way of questions in the chat box. Yeah. Okay, so if you adopt the density inhomogeneities that are present in the early universe, given to us by the cosmic microwave background, the CMB anisotropies are telling us the magnitude of these anisotropies and the physical scale of these anisotropies. Okay, so using that CMB anisotropy map as our starting point, if you simulate the unevenly distributed matter present in a volume, if you add those density inhomogeneities and simulate it and allow it to go under the influence of gravity, you naturally produce the kind of elementary structure that we see. Okay, so that seems to be a natural outcome of the initial density perturbations that are present in the universe. Under the influence of gravity, those density perturbations can grow, they can amplify, they can get amplified over time to end up in the kind of elementary and sheet-like structures that we see in the cosmic web. So that's what my short answer to the question, Sarang. So the only force at the large physical scales, the force that governs the evolution of the universe is gravitational force. So gravitational force is fed into these simulations, and the simulations are not interfered. You don't tinker with those simulations from that point. You have a homogeneous distribution of matter within a box. You artificially put in some density inhomogeneities within that volume of matter, and then you allow gravity to take over and run the show. So you automatically end up with these filamentary structures. So you are simulating how structure formation is likely to have happened in the last 13 billion year history of the universe, aided by gravity. Okay. Now the only point which I did not mention is that in these simulations, typically astronomers simulate dark matter. Dark matter, we know, interacts with itself and with baryonic matter, ordinary matter, via gravity. So dark matter is what astronomers simulate, and at some point of that simulation, when the filamentary structures begin to form, they introduce gaseous matter, ordinary matter into it, because otherwise the physics becomes too complicated. Because once you introduce gaseous matter, you have to account for other forces. Okay, you have to account for hydrodynamic forces. There can be pressure, there can be turbulence, etc. So computationally it becomes very intensive. So initially dark matter is simulated, and dark matter provides the framework for the assembly of ordinary matter into galaxies, galaxy clusters, etc. So that's the idea. Yeah. Right. Yeah. So the filamentary structure thins down. That's a very good question. So filamentary structure thins down. So the density corresponding to a given overdensity within this filamentary structure, it thins down as the expansion of the universe happens. Okay? So there are regions where the filament breaks down and voids are created, but these happen far away from the nodes where galaxy clusters exist. These happens, these breakdown of these filaments. In other words, the density in those regions fall down to such a low value that you can refer to it as a void. Okay, and that happens far away from galaxy clusters in the wispy regions of the intergalactic medium. Okay, so one does see that in these simulations with the passage of time. Yeah, thanks. There are a couple of questions that have popped up in the chat window. Ashwati is asking, could the universe be expanding due to anti-gravity? So I don't know what anti-gravity is. So Ashwati, sorry, I won't be able to answer that. Ashutosh is asking, since space is expanding, doesn't it mean size of galaxies will also increase? Okay, that's a very interesting question. So one common question that often comes is, if we say that space is expanding, okay, the universe is expanding because of expansion of space, then why is the distance between the planets in the solar system not increasing? Why are the distances between stars in the Milky Way galaxy not increasing? Or more simply, why is the distance between you and me not increasing? The reason for that is there is always a competition of forces. Okay, so let me try to answer that by taking a simple example. Okay, let's take the human body. When we stand here on the surface of the earth, there is a force of gravity on our feet. And depending on how tall you are, there is going to be a different force of gravity on the tip of your head. Okay, so there is a differential force of gravity from your feet to your head. So which means there is a change in gravitational force from the feet to your head. And because of that, ideally, one may think that we should get stretched. We should feel the tension because of this differential force. The reason why we don't get stretched because of this differential force between our feet and our head due to the Earth's gravity is because the molecular forces that bind the cells in our body together, the molecules that are present in our body, and the forces between those molecules overpower this differential force. That is why the human body remains intact. Okay, you take the human body you take a human being into a more extreme gravitational field, like in the vicinity of a black hole. The differential force between the feet and the head will be so strong that the gravitational force can overpower, the differential gravitational force can overpower the molecular bond that exists between molecules in the human body, and you can get torn apart. Can they show these kind of scenarios in science fiction movies, etc.? So there is always a competition between forces, and whatever we see as an outcome depends on which force is dominating. Now, in the case of planets of the solar system, the mutual gravitational force between the sun and the planet overpowers the expansion of space that is happening between the planets and the sun. So you can think of the sun and the planets as holding hands together. Okay, and somebody is stretching the fabric of space on which these planets and sun is located. Now, since the sun and planets are holding hands, even though the fabric that they are sitting in is stretching, the distance between them doesn't change. Okay. So in astronomy parlance, we will say that the solar system has decoupled from the Hubble flow. Similarly, if you take the stars within the Milky Way galaxy, they are all held by the gravitational potential of the Milky Way. So even though the space that this Milky Way is existing in is expanding, that mutual gravitational force between the stars within the galaxy is holding them together in this expanding fabric of space. So we will say that the Milky Way has decoupled from the Hubble flow. If you look at the local group of galaxies, Andromeda galaxy is coming towards us. Andromeda galaxy spectrum will exhibit a blue shift, not a red shift. That is because this local group is a gravitationally bound entity. All the galaxies in the local group, the 50 plus galaxies that are present in the local group, including Milky Way and Andromeda, they are all moving within the gravitational potential of the local group. So for an astronomer who is sitting on Milky Way, if the astronomer were to only measure the galaxies within the local group, he or she will never come to the conclusion that we are living in an expanding universe, because the local group has decoupled from the Hubble flow. We have to observe galaxies that are outside of the local group, like in the Virgo cluster, like in the Coma cluster, like in the Fornax galaxy cluster and other parts of the universe, to come to the realization that we are living in an expanding universe. Similarly, if you are an astronomer in one of the galaxies in Virgo cluster, if you only observe galaxies within the Virgo cluster, you will never come to the finding that we are living in an expanding universe, because the galaxies within the Virgo cluster are all moving under the influence of the local gravitational potential. All those 1,500 galaxies in the Virgo cluster have decoupled from the Hubble flow. Okay. For those astronomers in Virgo cluster, they have to look at Milky Way, Andromeda, Fornax galaxy cluster, Coma galaxy cluster, and other distant galaxies to see the expansion of the universe. So there is a competition between forces. Wherever gravity overpowers the expansion, we don't see the expansion immediately. Okay, but large distances, gravitational force is very, very less. Okay, so the gravitational force between Milky Way and the galaxy in Virgo cluster is almost negligible. I mean, negligibly small, almost zero. So at that scales, we will begin to see the expansion of the universe. So galactic cluster is smallest entity where expansion becomes observable. Outside of galaxy clusters, Ravi Kiran, your question is, are galaxy clusters the smallest entity where expansion becomes observable? My answer is beyond galaxy clusters. Okay, you have to observe beyond galaxy clusters. So our local group is one small grouping of galaxies. We can observe other galaxy clusters, galaxies in those clusters, and we can see this expansion of the universe. Okay, so those are all the questions that are there.
Sir, I have another question.
Yeah.
So astronomers often talk about the hydrogen 21 centimeter line, right? Could you shed some light on that?
Yeah, so 21 centimeter is refers to the wavelength of a photon that is emitted by atomic hydrogen. Okay? In frequency, this corresponds to 1420 megahertz. And this 21 centimeter is used to study diffuse gas in the universe. It's also used to study gas in distant galaxies. Okay, so 21 centimeter, that wavelength corresponds to the wavelength of a photon that is emitted from atomic hydrogen's hyperfine energy levels. So atomic hydrogen has a proton and an electron, and these two particles have spins. Now the spin vectors can be either aligned or they can be opposite to each other. So the spin vectors can be parallel to each other or they can be anti-parallel. This parallel versus anti-parallel configuration has a slight energy difference which corresponds to roughly 10 to the minus 6 electron volt. So just to remind you, the gross energy levels in hydrogen atoms have several EV, electron volts of energy difference. Okay, first ground state, first excited state, etc. Now we are talking about not just fine structure, we are talking about hyperfine structure energy levels, where the difference in energy between the parallel spin and the anti-parallel spin of the proton and electron has an energy difference of 10 to the minus 6 eV. So a hydrogen atom where spin is parallel, okay, where the proton electron spins are parallel, randomly it can change its orientation from parallel to anti-parallel spin, which is a lower energy state, and in that process it can release that photon corresponding to 10 to the minus 6 eV, which in terms of wavelength corresponds to 21 centimeter and in terms of frequency corresponds to 1420 megahertz. So these photons, you can never observe this in laboratory because the chances of the spin flip happening naturally is very, very small. Okay? The half-life is really large and the atom has to be left undisturbed for this. If a collision happens, then collisional de-excitation can happen, which will not result in the release of a photon. Whatever particle collided will carry away this energy. So this is spontaneous spin flip. Okay? And this, in universe we see this, and this is a great way to trace atomic hydrogen in our universe, which is not emitting light. Okay? That's what 21 centimeter is.
Yes, sir. Thank you, sir.
Yeah, there are a couple of more questions. Maybe I will take one last. question. Difference between Doppler shift and cosmological redshift. I think I explained this in the presentation. In terms of observation, we record the spectrum, we see spectral lines moving, shifting. So we don't find them where they are supposed to be, we find them at longer wavelengths. That is what redshift is. That shift can be produced by either the source moving relative to us or because of the expansion of space between us and that source. Now, if we are talking about local distances, then the redshift can be interpreted as Doppler kinematic redshift. Okay. But when we are talking about distant galaxies, the relative velocity term itself does not have any meaning. For example, what is the relative velocity between Milky Way and a galaxy that is 300 million light years away from us? The problem is that when we are looking at a galaxy that is 300 million light years away from us, we are getting light that started off from that galaxy 300 million years ago, which means we are looking at the past of that galaxy. So how can we talk about relative velocity? It's like asking what is the relative velocity between you and me when you crossed my street yesterday. Okay, what is my velocity now today and your velocity when you crossed my street yesterday? Okay, these are two events that are separated by time. So the concept of relative velocity exists only for objects which are in the same local reference frame. So therefore, we cannot interpret the redshift that we see in the spectra of distant galaxies as due to their actual movement. Instead, those redshifts are interpreted as due to the expansion of space, and it is given this name cosmological redshift. So I think I'll stop my Q&A here.
Yes, sir. Once again, thank you very much for giving this wonderful talk, taking out your time in your busy schedule to give this talk. And I thank all the audience for attending this talk, and hopefully we'll be able to give talks in the future as well.
Yeah, thanks Arjun for having me over, and thanks Parsec. This was good, and I hope I will get to meet you all physically in 2021.
Yes, sir. Sure, sir. Thank you, sir.
Thank you. Yeah, thanks.
Thank you, sir.